actually gave us a really good in the list of what we need. The two things, if you don't know, I don't think you need to look into too much. They're not too hard, but it's generally not that important, is empirical formulas and percent relative abundance, because that stuff barely showed up on the final. I think there was like one question for each, so that was relatively insignificant. I think, okay, the things that fucked me over the most that I didn't study for were equilibrium, specifically manipulating equilibrium equations. This one I wasn't prepared for. A plus B becomes C, A plus B turns into C plus D is KC1, and C plus D turns into A plus B is KC2. For that, it's 1 over KC1, if that makes sense. I'll send screenshots of notes to make more sense, but manipulating the equations was not like a thing that I was prepared for. Same with KP and KC. There was a question on there where you need to find KP, there was a few where you need to find KC, and there was one where you need to find there's 5 equations, and you need to find the one that has KP equal to KC. The formula for that I'll send as well. That one is relatively simple. I just wish I knew it in the moment. It's delta H. Positive delta H means exothermic, which means heat comes on the product side, and then negative delta H means endothermic, which means heat is on the reactant. I think of it as positive H. The plus looks like an X, an exothermic, and then for minus, I look into endoskeletons. I don't know why. As well, this one I feel like isn't that crazy. I think it's relatively intuitive. Is the Chatelier principle with pressure, temperature, catalyst, stuff like that. K greater than less than and equal to K. Q greater than less than equal to K is also relatively simple. For acids and bases, everything here makes relative sense. You really especially need KSP and molarity. Okay, so I remember one question that messed me up a little bit. There's a lot like this. I chose to remember this one because it's the simplest, and then I do that a lot for quizzes so that later I can come back to it. Lead bromide has a KSP of 2.17 times 10 to the negative third. I hope that's readable. And so the way that KSP works is like a mole ratio. Right here. So if we get lead bromide here, it breaks down into lead ions and then 2 bromine ions. And so I'm going to write KSP as S just for a variable. Because it's a mole ratio, there's one lead bromide for every lead, so this is just going to be 1s, and there's a 2 to 1 for bromine, so it's going to be 2s, just like this. And then, so, your KSP equation is going to be your reaction, let's say this, it's like A is made up of B plus C. Yeah, I'll do this. Your KSP, your KSP of A, let's say that's what you're given, your expression is going to be B, concentration of B multiplied by concentration of C, and they're each raised to the power by their coefficient here. So for here, it's going to be KSP is equal to concentration of lead ions times the concentration of bromine, and because there's 2 of them, you're going to square it. And then to put this back into S, just like, so that's less of like a case-by-case basis, if that makes sense. Lead is 1s, and then I'm going to put 2s here, even though I don't put it here, just like, keep it in mind. And so, algebraically, it would be 2s cubed equals KSP, or 2.17 times 10 to the negative third, and then from here you can just solve for S, so that's going to be, and then cube root it, hold up. Yeah, and so here, S is equal to 0.103, rounded up, molarity, and so, this is how you do KSP. That messed me up a lot. I'll do it less of a case-by-case basis, more of like a, just like to show you a formula, so I'll get rid of this. We'll say that the KSP of A2B3, we'll just put KSP as X, so it'll be A2B3 becomes 2A ions, there's a charge here, and then 3B ions, there's a charge there. So the mole ratio is X, 2X plus 3X, and then remember, give me a second, yeah, I'll write this down. This was also, what I'm writing down now, I put in my note card, and next card, I'm going to send that too, just to make things, I don't know. So the way this works is, it's going to be raised to the power of its coefficients, multiply reactants. Just like this. And so we're going to do that right here. We'll have KSP equal the concentration of A to the second power plus the concentration of B to the third power. And then when we put that as our X, actually I could have put S because that's more common, but it's fine. Oh yeah, I'm going to use S for solubility. Sorry, my mistake. So our KSP is X, and our solubility is 2S because there's 2A ions squared plus the concentration of 3s because there's 3 B ions, and then so algebraically this would just be 6s to the 5th. I don't think there's ever anything that's complicated with like to the 5th power and stuff, but this is just the example I gave, and then like going more in depth to it. This is one of the things I fucked up a lot on. I blanked on it completely, so I would put this on my note card if I could go back in time. There's also one thing I didn't know if I needed to. I just put it down to space. I'm glad I did. Is oxidization. There's a few questions in there where you need to know. You need to identify what element in a reaction is being oxidized or reduced. There's ones where it gives you like 5 reactions. You need to find out where reduction is happening in that reaction. And for that, I have a lot of that on my note card. I'll send that. Okay, so redox. It's not too complicated, but it's like it's its own thing, low key, if that makes sense. So, oxidization is the loss of electrons. So in that sense, if something's being oxidized, you can tell if the oxidation number goes from like 2 to 5, positive 2 to positive 5. That means it's increasing, and because if you remember, electrons are negative. it increases, it's being oxidized because electrons are negative. So then we have reduction, which is the gain of electrons. So think about it like if it goes from positive 2 to negative 1, it's getting more negative. There's a thing, oil rig, I don't want to write it all out. Oil rig, OIL, oxidization is loss, rig, reduction is gain. Yeah, that was something this recorder taught us. So to give an example, we'll go 2 sodium plus Cl2 makes 2 NaCl. Now, one thing that's important is these are ions. So these are free elements. See how there's no charge here, if that makes sense? Yeah, I'll explain right here. This is sodium. It has a charge. That means that it's an ion, right? This is sodium, but it has no charge. That means it's a free element, or in this case, in sodium's case, a metal. And so these have an oxidization number of 0. So for this one, the number equals the charge, aka +1. For this one, there is no charge, so the number equals 0. So right here, you'll see the oxidation number of sodium is 0. Cl, chlorine here, is also a free element, so it has no oxidation number. Here, they bond, right? And so they need a charge to bond. So sodium gains a +1 charge. Chlorine gains a -1 charge. Is that it? I hope that makes sense. I'm going to bring these up here. So here, it went from 0 to +1. That means it was oxidized. I know it's kind of small. I'm going to send individual photos of the full page later. And so here we have chlorine. Chlorine goes from 0 to -1. That means that it was reduced. If that makes sense. I'm going to look at my note card for this because I will keep like oxidation number rules on my note card, and it helps out a ton. So we have oxidation. Okay, so for the first, every time you see a hashtag, it's just going to mean the oxidation number. The oxidation number must add up or equal to its charge. And you'll see that in an example later. You also see it here with the sodium. The oxidation number is 1 because the charge is +1. The next one is free elements. Right here. Free elements have a number of 0. Next, this is where things, actually, ions have their number equal to their charge. Again, as you saw with sodium. Then now we get into the more specific things. So for hydrogen, the number is equal to +1 unless it's with a metal, which in that case, it will become a -1. Using brackets, there we go. And for any halogen, their number is going to equal -1, just like their charge, unless, because, you know, signs of exceptions, unless they're with oxygen, which in that case, it will become positive, and that's very flexible. And then for oxygen, their number always equals 2-. Sorry, I should not be saying always. Yeah, their number equals 2-, and then these are the rules that I have down that I think are really good. Okay, so when it comes to balancing redox reactions, they're really tricky, and they're actually so tricky that this might be my 3rd time. When you're balancing redox reactions, there's a lot going on. There are 8 steps. I break it down into 8 steps. Your first balance reaction, not oxygen. I'm just going to put this as O2, not hydrogen or oxygen. Just because it's oxygen, ion, it doesn't matter. You get the idea. Now your second step is going to be write your half reactions right here. Then your third step is balance O2 with H2O. There's not actually O2. I just don't want to write. I could do O2 minus. Yeah. Okay, now your fourth step, balance hydrogen with, you guessed it, hydrogen. For your fifth step, you're going to balance charge using electrons. Your sixth step is going to be making electrons equal. You'll see that and what that means. Seventh step is adding your half reactions. And then finally, your eighth step is balance. So that's the order that you're going to do it in. And I'm going to grab an equation from my notes here. I think I should have. Where is it? See what the equation to do is so 2 minus plus Fe2 plus becomes Cr3 plus. Alright, so here is our first equation. Now, our first step is balancing everything except oxygen. So there's 2 chromium here and 1 here, so we're just going to double this. And for this one, that's all we have to do. So that was our first step. That's our first step of balancing everything but oxygen and hydrogen. And then now, the next thing we're going to do is we're going to make our half reactions. And that's simple when you know how to look for it. It's really easy. You have chromium here and chromium here, iron here and iron here. There's 2 things going on. There is these 2 chromium, then there's these 2 iron. Those are your half reactions. Cr2O7, 2 minus, becomes 2Cr3 plus, and Fe2 plus becomes Fe3 plus. And so that's your second of writing half reactions. Now, I'm going to do just one of these. I'm just going to do the top one for the sake of, to explain all these, right? All these. Anyways, here is your first half reaction. Chromate equals I think this is chromate. I don't know. This is Cr2. So this has 7 oxygen, and this has 0 oxygen. So we need to add 7 waters to balance that out. That's our third step. Balancing oxygen with H2O. Then next, what we're going to do, we have 14 hydrogen here, and so there's none here, so we need to add 14 H plus ions. That's your fourth step. There, you balanced hydrogen with H plus ions. Okay, now your fifth step, you're going to balance the charge. So here, your charge is positive 12, and here your charge is positive 6. So you need to lower this down to 6. You do that by adding 6 electrons, which is basically taking off 6 charge. That's your fifth step. You just balance charge by adding electrons to one side. Now let me go do this for this. Let's go do this for the second reaction. This one is really easy. There's no oxygen, there's no hydrogen, it's just a difference in charges. So this one is going to be electron plus Fe2 plus becomes Fe3 plus. Sorry, that's on the wrong side. Simple as that. And then now you're going to balance, or you're going to make your electrons equal in the way you do that. So now you're going to make your electrons equal. By that, that means this has 1 electron, this has 6. You need to multiply this by 1, and well, there's something here in the way. It's going to be multiplied by 6, okay? So you're going to have 6 iron, 6 electrons, and these are going to cancel out. Right here, you have your 6 electrons that are going to cancel out, and I don't need to cross out anything or like change anything because it's times 1. Nothing really changes. That's your sixth step. You equalized the equations by using the electrons, if that makes sense. I don't know what the full terminology is. Now you're going to add your half reactions. You're going to take reactants from here and reactants from here before you move on to the products. So take reactants from this one, 6 iron, we're done. Now move to this one. And now you can ignore electrons. Now we get reactants, we take them from this side. We have 6 Fe3 plus, and we'll take some from this side, the rest from this side. There we go. Now that's your 7th step. Add half reactions. Just like that. Now we're going to balance it all out, and we can do that by doing this. Right, so normally, for other ones, you'll see that both sides have some hydrogen and some oxygen. So normally you would need to cancel out some on both sides, and you'll probably see that because I'm probably going to do an example problem. But in terms of balancing, this is mostly already balanced. Look, so we have right here 14 hydrogen here, then we have the 7 and the 2. That makes both sides have 14 hydrogen. This side has 7 oxygen, and that's it. This side also has 7 oxygen. And then after that, what's up here? Anyways, that's great. Now let's look at the charge. This side has a combined charge of, this is 12, this is 14, this is -2. So this side has a total charge of 24. It's not 24 electrons, I'm just, no charge, I guess. This side has 18 right here, 6 right here, and 0 right here. You add that, you get 24 charge. How simple, how perfect, how absolutely easy. This was in an acidic solution. It's different when it's in a basic solution, because, you know, why would it ever be consistent? So I'll take this one, SO3 2 minus. Yeah. So now we're going to do this in a basic solution. Here is our equation. It is SO3 2 minus plus NNO4 minus becomes SO4 2 minus plus MnO2. So for basic solutions, you're going to repeat 1. Yeah, repeat 1 to 5 the same. But now you're going to add 1 hydroxide to both sides for every H, right? Let me start. Perfect. Add hydroxides to both sides for every H. and just like that. That is the only difference. So we'll do this again. I don't think I need to do this in red pen until we get to this step. So is our equation balanced? 1 sulfur, 1 sulfur, 1 manganese, 1 manganese. It's fine. We can ignore the oxygen for now. So we'll make our first half reaction. MnO4 become MnO2. So this side needs 2 oxygen, so we'll give it 2 waters. It now has 4 hydrogen that this side doesn't have. So we'll give this 4 hydrogen, just like that. And now we need to balance out the charge. This has a charge of 3. 4 from here, minus 1 from here. This has a charge of 0, so this means 3 electrons. Now, that's steps 1 to 5. We need to add 1 OH for every H. So because we had 4 H's, we're going to add 4 hydroxides. And then we will simplify this at the very end, because this can't be 4 water, and then that can cancel out with this water, but we'll save the simplification until the very end. We've got a second half reaction going. SO3, 2 minus, becomes SO4, 2 minus. This side needs an oxygen, so we'll give it 1 H2O. Now this side needs some hydrogen, so we'll give it 2 hydrogen ions. Charge. This side is a 2 minus, this side is a 0, so this needs 2 electrons. And now, there were 2 hydrogens added, so each side is going to get 2 hydroxides added on. And remember, this is only for basic solutions. So from here, we can continue on like normal. We have 3 electrons here, 2 electrons here, so we'll do that. That will give us 8 hydroxides, cancel out the electrons, 8 hydrogens, 2 MnO4s, 2 MnO2s, 4 waters, and 8 hydroxide here. Now on this bottom one, this will give us 6 hydroxide, 3 waters, 3 sulfites, 3 sulfates, 6 hydrogen, no more electrons, and 6 hydroxide. Now we're going to add them all together, and I'm gonna make it a little bit bigger so that there's no confusion. We have 8 hydroxides plus 8 hydrogen plus 2 MnO4 minus, as well as 6 hydroxides, 3 waters, and 3 sulfites. Then we get to reactants. It's going to be 2 MnO2, 4 water, 8 hydroxide, 3 sulfates, 6 hydrogen, and 6 hydroxides. This is before we simplify it, so it is going to get easier. It's a good thing it is, sorry. So we can group these ones. The hydroxides and the H's will make water, and then we can group this into 8 H2O, which we can also group into the water here, and we'll do the same on this side. Yeah, this is going to be 6, actually, yeah, so this will be 6 H2O, and we'll group that into the, sorry, that's not the water right here, right. So we'll go on, simplify this. The basic, when they're in basic solutions, they do take some extra time, and the charges get really weird, especially because you're adding hydroxides after you've already balanced electrons, so it gets a bit weird, but in the end, it all works out, and these take a bit of practice. Right, so now we've grouped up some of these things, and now we can start canceling things out. So we have 6 hydroxide over here, and 8 here. We can cancel this and make it 2, and remove all these hydroxides. We have 11 waters here, and 10 here, so we can make this 1, and cancel out the water there, right? Now we can clean this up a bit. Okay, now we'll take a look. Right here we have 8 oxygen, 1 oxygen right here. We have 9 oxygen right here, and that's going to total to 18 oxygen on the reactant side. Now right here we have 4, we have 2 more over here, and we have 12 more over here. And this is going to also add up to 18 oxygens. So that works out. Now we have 2 hydrogen over here, and 2 hydrogen over here. It's getting a bit messy, that's fine. 2 hydrogen, that would check out. 2 manganese, 3 sulfate, 3 sulfur, that works out fine. Now we gotta get the charge. So this is -2, this is 0, that's a -6, so this will be -8 charge. This is a 0, because it's neutral. This is a -2, this is a -6, that gives us a -8 charge. And that is your, that's your redox solutions, balanced and basic. This is a lot, I know, but I'm gonna put in some practice problems when I send this. Honestly, after that, it got pretty simple in regards to everything else. Iceboxes, oh, Ka and Kb, that one was really important. That, well, yeah, it was on the, Ka and Kb was on the FRQs. Off loose memory, you're given the concentration of hydrogen and like another element, you're given the concentration of those, then you need to, from there, you need to find Kb using just that. I don't remember if volume is included. I'm gonna go over, so Ka and Kb, low-key a doozy. Now, the easiest way you can do it is, if your thing is at 25 degrees Celsius, and you're given, let's say you're Ka, you're given Kb, then because, Kw is always 1.0 times 10 to the negative 14th at 25 degrees Celsius, you can, and because Ka times Kb, this also has to be at 25 degrees Celsius, Ka Kb at 25 degrees Celsius equals Kw. So let's say in this problem, it tells you it's 25 degrees Celsius, and you're given Kb, which I never got one of those. You can simply solve by just divide, it's Kw divided by Kb. Yeah, so Ka equals Kw. Or Kb, and this is also vice versa, so Kb equals Kw divided by Ka at 25 degrees Celsius. I never got one of those, so we're going to go off an example problem I found online. God, okay, so Ka is a lot, so the whole problem I found was a 0.175 molarity solution of an unknown weak acid, Ha, has a pH of 4.27, find Ka. Now, for my MCQ, I think everyone got the same MCQ, but different FRQs. I know there are at least two, so mine didn't give me pH, but I did know what the acid was, so that helped me out. This is a little bit different, but it's fine. So to find Ka, well, first we'll do our equation. Ha becomes H plus A minus, simple as that. So for Ka, you need, it's very similar to everything else we've done before. You need concentration of hydrogen and then concentration of your salt or conjugate base. And then you're going to divide it by acid. Now, one thing I did mess up on is this is initial concentration. Ka is talking about at equilibrium. Ka is at equilibrium. So you can't use initial, because that would be like, that's a Q, right? So for these, you need the concentration of your hydrogen, the concentration of your salt, and the concentration of your acid. Just like this. So to find the concentration of hydrogen, if you know your acid, you can just, if you know your acid, you can just do the negative log of that. But because we have pH, we can find the concentration of hydrogen with 10 to the negative pH. So that would be 10 to the negative 4.27. Let me just do that real quick. So your concentration of H, using pH, we found that the concentration of hydrogen is going to be 5.37 times 10 to the negative fifth. And because hydrogen and the hydrogen and the salt are 1 to 1, you know that both of these are equal to 5.37 times 10 to the negative fifth. Now, even though this is also a 1-to-1 ratio, that's not going to work the same because the acid has its initial concentration. So you need to do an icebox. So I'll just set it up again. This should be that kind of my fault. And so we know the initial is 0.175, and this is at 0. So we're going we can just do the x's here. So we can do minus x plus x plus x. And because all of this is in molarity, so if H and salt equal x for their molarity, then we, because okay, sorry, this is a bit hard to understand. If the concentration of H is x, and we just found out that the concentration of H is 5.37 times 10 to the negative fifth, then we know that that also equals x. So this, even though we can solve for this, even though we don't know KSB, normally you can't use x's when you don't know KSB, because then you're using a variable, and you're solving against another variable. But because we solve for x, we don't need KSP. So the concentration of the acid here, 0.175 minus x, turns into 0.175 minus 5.37 times 10 to the negative fifth, just like this. Let me solve this real quick. 5.37 times 10 to the negative fifth, 1.175, nice. Okay. So rounding up, the concentration of this weak acid is 0.175. Well, okay, technically, I can't round. It's gonna be 0.749. Even though they're genuinely the same, I accidentally rounded up to it. It still matters that you just solve for it in this way, because in another equation it might be a more dramatic change. So now that we know the concentration of our acid is 0.1749, we can finally do our Ka expression. So concentration of hydrogen times the concentration of its acid divided by the concentration of the weak acid. That's going to equal 5.37 times 10 to the negative fifth squared, because it's just the same thing here. This is just x times x, so that's just x squared. And then the concentration of your acid, 0.749. And so when you divide that, or when you solve that, you get your Ka equals to 1, 2, 3, 4, 5, 6, 7, 8. No, wait, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, K equals 1.6 times 10 to the negative 8th power. Just like that. And you can, so yeah, for Ka and Kb, it was like a mind fuck trying to find out, not knowing how to do it with only knowing my concentrations. But you need concentrations to find Ka. So when you're given some concentrations, it makes the rest of it easier. For the problem I had on my FRQs, I was given, I don't remember the exact problem, but I was given the concentration of hydroxide, and then I think I was given the concentration of the salt, and I had to find Kb. So basically just the same process, but basic. And so if you know your concentration for your hydroxide, or your H or whatever, you don't need pH at all. But if it's an unknown acid, which maybe it's like that on the other FRQ, it's better to use pH to find the concentration of H, because your unknown acid could be something like acetic acid, where the concentration of H is tricky to find out at initial molarity. I hope this helps. After that, though, it's relatively calm. You just need to make sure that you're okay with everything that's listed on here. In my opinion, MCQs were focused on chapters 2, 3, 4, and 5 for a lot, and then a little bit of 14 to 17. I'd say there were no acid-base titrations on MCQs. For FRQs, there's 40 MCQs, by the way. For FRQs, it's one double-sided page. It was one problem for redox, and then everything else was just 14 to 16. So for FRQs, I don't know what the I don't know how much each is worth, but for FRQs, if you know 14 to 17 pretty well, you should be fine, and you just need to know your redox. For MCQs, it's more like all of this stuff, but it's like a little bit of everything.